Hola, hi, this is Al, your statistics instructor. In this video, we will provide a proof of one of the most important results in probability and statistics, the central limit theorem, also known as CLT. Well, let's get to work. So, as I said, the main goal of this video is providing a mathematical proof for that very important theorem, the central limit theorem. Okay? But in order to show that result, we are going to rely on a couple of results. Okay? This one here, it's Theorem 7.5 from your textbook. We are going to be using this theorem, but we're not going to be showing it. Okay? But basically what this theorem says is the following. If you have a sequence of random variables and the limit of the moment generating functions, or the sequence of moment generating functions, converges to a particular MGF, then what we have is that in the limit, right, the sequence of random variables that we have here, y1, y2, y3, blah blah blah, yn, as n goes to infinity, what we have is that the distribution of that sequence is going to be the one of the limiting MGF. Make sense? So for instance, if you have a sequence of random variables, right, and then as n goes to infinity, you realize that, you know, in the limit the MGF looks like the one for you know, a normal, then what that means is that the limiting distribution of that sequence is normal, right? So that's exactly what we are going to be doing here. We're going to be using MGFs to show that the limiting distribution, right, of a sequence is normal. Okay? Something else that we're going to be using from calc is Maclaurin series. Okay? So a function, right, in this case a function of x, could be expressed as a sum of polynomials, basically, right, around 0, like this. The function evaluated at 0, f at 0, plus first derivative, f prime at 0 times x, f double prime evaluated at 0 divided by 2 factorial times x squared, and so on. F triple prime evaluated at 0 times x cubed divided by 3 factorial, so on, right? And you keep going, right? So in the limit, these guys are the same. If you truncate the approximation, then it is just an approximation. Okay? But in the limit, these two, right, the left-hand side and the right-hand side, are the same. It's an equality. Okay? It's an equation. Okay. So now, armed with Theorem 7.5, right, that you know, has to do with MGFs and the limit of the sequence of MGFs, and this machinery from calc, Maclaurin series, we are going to be able to show the central limit theorem. One more thing. We are going to be using MGFs, and these properties that I'm showing you right here will be important. Okay, so first, for any MGF, if you evaluate the MGF at 0, then that should be equal to 1, okay, for any MGF. Now, as you know from sta258, if you take the first derivative with respect to t and evaluate at 0, then that equals the expected value of your random variable. If you take the second derivative with respect to t of your MGF and evaluate at 0, then you obtain the expected value of y squared. Okay? One more thing. If a is a constant, right, and you find the MGF of a times your random variable y evaluated at t, that is, just by definition, the expected value of e to the power t times ay, which you could think of as the expected value of e to the power a times t times y. But that happens to be the MGF of just the random variable y. But now, instead of evaluating at t, you are evaluating at a times t. Okay, so that will be, all these properties will be useful during our proof. Okay, here we go. Now let me show you the statement of our theorem. So we have a sample, simple random sample of just a random sample of random variables x1, x2 up to xn, right? They are independent, identically distributed, right? Meaning that they have the same distribution, and all of them have the same mean, right? That's why we say they are identically distributed. And variance sigma squared is finite. Okay, there are a few random variables out there for which that condition is not satisfied. The variance is infinite. Anyway, so we have, as I said, a sample of random variables of size n. So they have the same distribution, they have the same mean, they have the same variance, and the variance is finite. Now we define a transformation, let's call it u sub n or un, right? And it's going to be given by x bar, the sample mean of these guys, meaning the sum of x1, x2, xn divided by n, right? That's x bar, the sample mean, minus its mean, mu, divided by sigma, divided by the square root of n. Okay? So, it turns out that as n goes to infinity, the distribution of un converges to a standard normal, meaning a normal with mean 0 and variance 1. Okay? That's what the central limit theorem says. Now, note that it is a very, very general and very powerful result, because all that we're saying is, the mean and the variance must exist, must be finite. And then you go, hey, so these guys could be binomial? Yeah. How about geometric? Yeah, no problem. How about exponential? Yeah, they satisfy these conditions. And then if you are interested in the sample mean, this transformation of your sample of observations, if you're interested in x bar, the sample mean, it turns out that if your sample size is big enough, it will be well approximated by a standard normal. Okay? So it's really powerful, really general. Okay. Anyway, let's start our proof. Okay? So the first thing that we're going to be doing is we're going to try and re-express that un, right, in terms of in terms of random variables that have a mean 0 and a variance 1. That will be useful. Okay, so first let me remind you what un looks like, right? Because what we're saying is we're interested in the behavior of that transformation un, right? Okay, so let me rewrite it here. Un or u sub n is going to be just sample mean of those guys, of those n observations, minus the mean mu divided by sigma divided by the square root of n. Now note that another way of expressing this would be just this numerator here, sigma here, and then just we will put that square root of n here. It's the same, right? I'm just doing a little bit of algebra. Instead of placing that sigma divided by the square root of n, that's the same as that square root of n here, right? Okay. Now, as I said, we would like to re-express these guys. Well, this guy, un, our transformation of interest, in terms of a sum of random variables that have a mean 0 and a variance 1. It will be very useful to do that. So let's define a new random variable, okay? Which is just going to be basically standardizing our x's, right? X has mean mu, x1 has mean mu, x1 has variance sigma squared. Well, then if we do this, x minus its mean divided by its standard deviation, well, that clearly will have a mean of 0 and variance of 1, right? You could just take the expected value, right? And you would be able to see that expected value of the CIs that we just defined is going to be 0 and the variance is going to be 1, right? No problem, right? We can see that the expected value of this guy is going to be 0. And the variance is going to be 1. Right? Okay. Now, what we're going to be doing next is trying to rewrite un in terms of the CIs, these new variables that have a mean 0 and variance 1. Okay? Okay. So, let me copy paste this, right? Let me just leave the second part. Okay. Now note that x bar, right? Let me leave this guy here. Note that I could factor out that sigma here, right? Now, note that x bar is the same as summation of xi's, right? Divided by n. Agreed? And what we had here, mu, well, you know, mu could be thought of as just, you know, n times mu divided by n. Agreed? Right? Okay. But now, note something interesting. This, right, what we have here, would be the same as this. So instead of having n times mu, I could absorb that here right? Summation of xi's minus mu is the same as summation of xi's minus n times mu, right? And I'm just dividing by n, that's a common denominator, so just re-expressing this, right? Now, what we could do here is this guy, right? I place it inside, and this one I pull it outside. Let me place that n here, and this one inside, right? Now this guy is a common factor, so now let me rewrite this as follows. Now right? That's the same. It's just a common factor, so I place it inside, so it's the same. And now let me simplify a little bit. Here we have square root of n divided by n, so what I end up with is just 1 over the square root of n. Agreed? Right? Make sense? Okay, but now these guys here, right, xi minus mu divided by sigma, that's the zi, right, that we defined. It's a random variable with mean 0 and variance 1. So now what we have is that, let me write it down like this. 1 over the square root of n times the summation of the zi's. That's un. Okay, makes sense. So let me call that equation 1. Okay. So at this point, what we did is we re-expressed the transformation in the statement of the central limit theorem, CLT, right? And we rewrote, re-expressed that UN variable, that UN transformation, as the sum of random variables with a mean 0 and variance 1, right? That will be really, really useful. Okay, so now observation, an important observation. If you want the moment generating function of a sum of random variables, say for instance something like this, z1 plus z2 plus dot 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 plus zn, right? So my random variable of interest, if my random variable of interest was the sum of the ci's, then by definition, right, the MGF is just e to the power t times, you know, my random variable of interest, which would be the sum of these guys. Okay. Now, since the x's are independent, the z's would be independent as well. Okay. So anyway, this is the same as this, just doing a little bit of algebra, right? We end up with this. Right? Oops. Let me fix that. Right? Just doing algebra, right? E to the power t times z1 plus z2 plus dot 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 zn is the same as this. Now using the independence between the z's, right? What we have is just the product of individual MGFs. So it would be just, since they are independent, the expected value of a product is the product of expected values. These guys here are by very definition, right, the MGFs of Z1, Z2, and Zn, right? Now, they are identically distributed, right? So meaning that the MGF of, well, the distribution, meaning the family to which they belong to, say that it was binomial, right? Then this guy is binomial with the same parameters. This guy is binomial with the same parameters. This guy is binomial with the same parameters. So the MGF of all of them are the same. They are identically distributed. So what we have here is the MGF of, let me call that a generic guy, a generic Z, a Zi, any of them, right? Evaluated at t. But then you have that n times, so you have that MGF to the n power. Make sense? Okay. Now note that we want the MGF not of the sum but of a constant times that guy, right? Because what we said is, hey, we're going to be using that theorem 7.5, right, to show what we want. But the thing is, we want the MGF of un, right? But un is not equal to the sum of the zi's, but it is equal to a constant times that, right? Okay, so let's write that down. We want the MGF of un right, evaluated at t, but that happens to be the MGF of that guy, the sum of the zi's, right, multiplied by 1 over the square root of n, right? So let me write that down. It's the same as m of 1 over the square root of n, and instead of writing this down like this, I'm going to be using the sigma notation, the shorthand notation. Sum of the zi's going from 1 up to n zi's, right? Okay, but now let's see those properties that we mentioned. If you evaluate the MGF of a constant times a random variable y at t is the same as the MGF of just y evaluated at a times t, right? So we already have the MGF of the sum of the zi's, and it's this guy. But we want to evaluate not that guy, but a constant times that, right? So this, right, will be the same as this. This is the MGF, to be super clear, what we have here, right? What we have here is the MGF of the summation of the one that we have here, right, is the MGF of the summation of the zi's, right? Evaluated at t. But we want something that is almost that. Well, this constant times that. And what we're going to be using is this property, right? So what we're going to have is the MGF of the original random variable. In this case, the original random variable will be the summation evaluated at a times t. And here the a is 1 over the square root of n. So this is what we're going to be having. Just divide by the square root of n here. Make sense? Okay, now this is where the idea of re-expressing un in terms of the zi's, the variables, the random variables with mean 0 and variance 1, is going to be really, really useful. So recall that the mean, well, the mean of those random variables is 0, right? So on one hand, what we have is the MGF of zi's, right? This should be prime, right? Because we want the derivative at 0 is going to be the expected value of zi, but that we know is 0, right? Okay, and also, right, we know that if we do something like this with the second derivative, what we're going to have is the expected value of z squared. But since the expected value is 0, that is the same as its variance, right? Because remember that the variance is expected value of your random variable squared minus the expected value of your random variable, the whole thing square. But if the expected value is 0, 0 square, 0, right? So this guy happens to be the variance of zi. And that we know is equal to 1, right? By construction, by the way we constructed these variables, right? Okay, making progress. Finally, remember that we talked about the Maclaurin series of a function. We're going to express the MGF as a Maclaurin series. Okay? So remember, it's just a function evaluated at 0, derivative of that function evaluated at 0, and so on, right? Second derivative evaluated at 0 divided by 2 factorial times variable squared, and so on. Okay? So here we go. Let me show you what we have here. I think that it might be easier if I show you this. See, function evaluated at 0. In this case, the function that we are interested in is the MGF. So function evaluated at 0 times first derivative evaluated at 0 times the variable. In this case, the variable is t divided by 1 factorial. T squared times second derivative evaluated at 0 divided by 2 factorial, and so on, right? So we're just using that recipe, Maclaurin series, okay? Now, since, and remember the properties that we talked about, that any MGF evaluated at 0 equals 1. So we have that, right? Now, remember that m prime at 0, meaning the MGF, the first derivative of the MGF evaluated at 0, that gives you the expected value of your random variable. Well, in this case, the expected value is 0. So t times 0, gone, right? Now, m double prime zi at 0. That is going to be the expected value of ci squared. But that happens to be the variance. And the variance in this case is just 1. So we have a 1 times t squared divided by 2 factorial, which is just 2, right? And then the next one, we just, it's not that important to do anything with it, right? Anyway, what we have here is this, the mean and the variance, first and second moment with respect to the origin, okay? and that property of any MGF. Any MGF evaluated at 0 is going to be 1. Okay. Now note that that is just the MGF of a single ZI, but you want to evaluate that MGF not at t, but at t divided by the square root of n. So wherever we see a t, we're going to substitute a t divided by the square root of n. So 1, that's okay. T squared divided by square root of n square, that's just going to be n, and that's the 2 that we have here dividing. T cubed, instead of t cubed, we are going to have t over the square root of n cubed, right? That's going to be the same as t cubed n to the power 3 over 2, right? And that 3 factorial is just from the Maclaurin series. Okay, makes sense? And all this to the n power. Make sense? Okay, we are almost there. Now what you need to do next is, I'm sure that you have seen this, but maybe it's been a while since you last saw it. So this is an important limit, right? If you have a sequence Bn that converges to B, then the limit as n goes to infinity of 1 plus Bn divided by n to the m power is e to the b power. Okay? Now, I want you to think about this. See this guy here? What we could do is we could factor out an n, right? So we could have, what we're going to have is this guy here, 1 plus t squared divided by 2n plus t cubed divided by 3 factorial n to the power 3 over 2, and that's times the triple derivative of the MGF with respect to t evaluated at 0, right? So MGF triple derivative of its zi, right? Evaluated at 0. And so on. Note that we could factor out a 1 over n. Well, I could have something like this. Let me factor out a 1 over n here. 1 over n times this. So that's the same as 1 over n times t squared divided by 2. That's first term. This one would be n to the power 1/2. And then you could continue. All the other terms are going to have an n in them somewhere, right? Then you could think of this as 1 plus 1 over n. And this guy here in square brackets is our sequence Bn. Make sense? Right? Can you see it? Now all these terms we could keep going if we had n, if we had the fourth term of that Maclaurin series. Well, that one would have an n as well, right? So as n goes to infinity, note that the limit of Bn is going to be just this guy, t squared divided by 2, right? Okay, so the limit as n goes to infinity of this is t squared divided by 2. So what we have is something that looks like this, right? The limit as n goes to infinity of 1 plus bn over n to the n power, right? We are going to be raising this whole thing to the n power, because remember what we have here is this, right? This is just the MGF of one of them, the MGF of one of the ZIs, okay? Is this guy here, right? The MGF of one of the CIs is this, which is the same as this, right? To the n power. What we did here is we just re-expressed that MGF of a single one of them as this, 1 plus 1 over n to the b, well, 1 plus 1 over n times bn, that sequence, right? So what we have here is 1 plus bn over n to the m power, using that result and noting that the limit as n goes to infinity of this is just t squared divided by 2. What we have is that the limit that we wanted is e to the t squared divided by 2, which, if you remember, it's the MGF of normal 0, 1. Give me a sec and I'll show you in our textbook. Just give me a sec. So here, if we go to page 838 from our textbook, we have the MGF for a normal with mean mu and variance sigma squared. If we have a normal with mean 0 and variance 1, the MGF reduces to e to the t squared divided by 2. Okay? And you see that? Okay? So, bottom line, what we have shown is that the variable un that we defined here, right, x bar minus mu divided by sigma divided by the square root of n, given these very general conditions, right, just we have a sample from some distribution with mean mu and variance sigma square finite, right? As n goes to infinity, the distribution of that variable un will be well approximated by a standard normal, meaning a normal 0, 1. And the main idea to show this theorem was using that theorem 7.5, right, showing that the MGF, that the sequence of MGFs would converge to the MGF of a normal 0, 1, right, and using Maclaurin series, right, for the MGF. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.